You've understood your variables, performed some exploratory data analysis on your dataset, did some initial cleaning of the data, and now you are ready to go to the next step of the data science workflow, which is modeling. The most exciting part of the job, the time when magic happens. Hi, I'm Ioana, a senior data scientist, and in my previous video we've performed exploratory data analysis together on the heart failure prediction dataset. Now it's time to model our problem, which is a classification problem. We are going to use Python in order to train two classifiers, one white box classifier and one black box classifier, namely a decision tree classifier and a random forest classifier. We are going to try and optimize the models that we are training such that we increase their predictability power and ensure that they generalize well on unseen data. We are going to look at a metric that is common for both algorithms and then assess which one should we go further with. When modeling, it is very important to start by splitting the dataset into different groups for training and then set aside one part of the data for testing. You can also split in train, validation and test if you have enough data. But then one thing that you really need to make sure of is that you don't have data leakage. Data leakage happens when you use some samples also for training and then also for testing. And this can raise serious problems as you could report metrics that are much more optimistic than the reality and then have your ego suffer a lot when the model goes into production. So then let's just jump into it and perform some classification. The first thing that I want to do is load my dataset, which is a CSV file. It is actually the dataset that we previously cleaned on the heart failure prediction dataset. And this time I'm going to load the CSV file with the pickle library. For this I'm going to import pickle. I'm also going to import pandas, matplotlib and another visualization library which is called graphviz. And we are going to proceed with opening the CSV file. The name of the file is clean heartfailure.csv and I'm going to insert it here as a parameter. Then I'm going to specify that I want to read this file, or comes from read, as f. And now I'm going to name the data object where I'll store all this information, which is df from data frame. And now I'll just load it. And now I'm just going to check that my data loads correctly. Okay, so my data loaded correctly. It is a data frame, the data frame that I previously cleaned in the EDA video. Let's see how many columns it has and how many rows. Okay, so it has 299 rows and 14 columns. If you remember from the previous video, there were two columns that encoded the same information. I'm going to drop one of these columns. I'll only keep the death event column, and then I will also drop the time column because I don't really know what it means, so I don't want it to interfere with my analysis. In order to drop columns by the name of the column, we can just use drop. Here I'm going to give the list of the columns that I want it to drop. And I'm going to overwrite my data frame such that it excludes these two columns, and I'll check that it worked by printing the columns. Okay, I have an error. Okay, I also have to specify that I want to drop the columns, not the rows, and for this I'll use x is equal to 1. And now I can see that the time and that event s are not in my data frame anymore. What I need to do first, before starting modeling, is splitting my data into train and test. The test data points are going to be set aside such that I run my algorithm on them and compare the predictions against the ground truth labels of those data points. Before splitting the data set into train and test, or train, validation and test, depending on the use case, we first want to shuffle all the rows. If there is any ordering in the data points that might bias the algorithm, we make sure that we break it. Then we need to be sure that there are no points that are being used for both training and testing. If this doesn't happen, if this doesn't hold true, then we see ourselves in the situation where we have what's called data leakage, and that is going to artificially increase the performance of our algorithm. We are just going to use method train test split. Now we are going to import it. In the data frame, we can call it. So this is going to be our y. The variable that we are trying to predict, and the x is our feature matrix. It is denoted by capital X because it is a matrix, so it is going to encode or contain multiple features, whereas y contains only one feature. It is a vector, so it's denoted by lowercase y. So we are going to select all the rows. This is data slicing that I'm performing here. We are going to select all the rows and all the columns except the last column, because the last column happens to be death event. Now, having the feature matrix and the response variable, we can perform the train test split by passing in our x and our y. We are going to set aside 20% of all our data as test data, and then we have another parameter, shuffle, which by default is set to true. I'm just going to specify it here once again to emphasize the importance of data shuffling. And then we can also choose a random state, which is basically a random seed that ensures that each time our split is going to be performed the same way. So the same data points are going to belong to the test set and to the train set. And this random seed can be any number. This method is going to output 4 objects. One additional thing I consider is important here is to make sure that this outputs what we are expecting. And for this, we are going to use some simple assert functions that can be used for testing. Here I'm checking if the number of points I have in my feature matrix for training is the same as the number of points I have in the response vector for training. I can also check other things, like for example that the total number of points I have for training and testing is the same as the length of my data frame, or that the number of points in the testing data set is 20% of the total number of points. So I have 239 points that I'll be using for training and 60 rows that I'll be using for testing. One thing that is also of interest for many algorithms is data balance. Let's see how our data set looks like. Here I'm just counting how many of my samples in train belong to the class false and how many to the class true. Now that we have our train and test data sets, what I would suggest doing, and what I've discovered is very beneficial on the long run in practice, is store this information in the data frame itself and save that information. This way you will have traceability and you will know which row is used for training and which row is used for testing. For this, we are just going to add a new column to our data frame that we are going to call scope. How I'm thinking to solve this task is first check the object that we created, yTest. So now we see here that for every response, true or false, we have also an index associated to it. So I'm going to extract all these indices, and I'll know that in my data frame at these particular positions I'll have a data point which is going to be used for testing purposes. I can extract the indices just like that. So now I have an index object, and I'll convert this index object into a list so I can iterate over it. Now this is a list, and I'll just name it test positions. Okay, so I have these test positions now, which I'm going to copy up here, and I'll be doing it like this. For position in. Here I'm just iterating over a list that goes from 0 until how long my data frame is, which here is going to be 299, and pos is just going to be one number, like 1, 2, or 299 or whatever. And now if this position is in my vector of test positions, I'll put a test in my scope column, and else I'll put a train. Okay, now let's see how this turned out. Good, so now I have a new column which is called scope, and this is populated with test or train according to whether the row is used for testing purposes or for training purposes. This gives me the advantage that now I can very easily extract some columns from my data frame and then display them visually. What I'm interested to do here is check the data balance by scope, and I can do it directly from a group by object. First, I'm going to extract two columns of interest from my data frame. That is the death event, which is my response variable, and the scope, whether the data point is going to be used for training or testing. Then I'm grouping them by scope, and I'm counting all the unique values. So this is going to give me a group by object. I see that for testing I have 40 rows for which that event is false and 17 rows for which that event is true. And now for visually displaying this, I'll unstack first the group by object, and then I'll create a bar plot out of it. This looks much nicely. So I see actually that during training, the number of rows that are having the label false is double the amount of those having the label true. So this is not very balanced, but also it's not horrible compared to like other situations that we might encounter in practice. For now, we are not going to proceed with any data balancing techniques. In this video, we just want to focus on choosing a classification model for our use case. The first model that we are going to try is decision trees for classification. I'm importing the tree module, which allows me to use the decision tree. The first thing I need to do when modeling with a decision tree is initialize the classifier. So decision trees can be used for both classification and regression. They also allow to pass here different parameters that are used to optimize the model. So now in order to train our model, we are just going to use the fit method, and we are going to pass the features and the labels. The features are in X train and the labels are in Y train. Now we have a model with which we can predict. Classification trees are really cool because they are white box, are very transparent in terms of how the decision was made to reach a certain result, unlike, for example, artificial neural networks, where everything happens in a black box and then only the result is output. We can actually visualize the decision process. By using plot tree, then I'll just use plot show to discard some output that is not helping. Okay, so this is how our decision tree looks like, but of course from here we cannot see much, and so in order to make everything more visually appealing, we are just going to use the GraphViz library. We are passing the model as a parameter. We want the boxes to be colored by class. For feature names, we want the tree to clearly state what feature it is using for splitting at a particular point. So we are just going to create a list of all the columns name and pass it here. And for the class names, we are just going to pass values of the classes we are working with, true and false as per death event. Pass in the dot data, our previously created object, and then graph render in order to save the graph in our PDF file, which we will call full tree. Oh, import graph is not defined. Of course, because it is a method in the tree package. Now we see here that we have the full tree PDF. Our tree looks like that. We can zoom in and really understand what happens at every step in the decision-making process. So this is the full classification tree. It is made up of nodes. The main or initial node is called the root node. The final nodes at the extremities of the tree are called leaf nodes. And then all other nodes that are in between and that are being split are called internal nodes. For now, we are just going to limit ourselves to predicting with this model that we've trained. I'm going to call my prediction object y hat, coming from y estimated or y predicted. And I'm going to predict on the test samples, and you can see here that I'm not passing the labels anywhere, so I'm just using the features. And then what I'll do with the labels afterwards is compare them against what I'm predicting now. How do my predicted labels look like? A NumPy array with true and falses, which is basically the same as my y-test, except that y-test is not a NumPy array, but it is actually Panda series, so I'll have to convert both to the same object. I can extract just the values and exclude the indices, like that. So now I have two objects, which are NumPy arrays, y-test and y-hat. And so in order to see how well my model performed, I'll have to compare these ground truth, which is the real labels of my test group, against the predicted labels for those particular data points. I would use a confusion matrix in order to compare the ground truth, which is y-test, and the predicted values, which are y-hat. And for this, I'm going to import confusion matrix. I'll pass the real values or the ground truth, and the predicted values y-hat. On the diagonal, 29 and 8 are the values that were correctly predicted. On the other positions are all the values that were not correctly predicted. From the confusion matrix, we can calculate the accuracy score. Manually calculating it, it would be 61% accuracy. But if we want to do this in a more elegant way, name our confusion matrix CM, so we can perform operations on this object. CM diagonal is just going to extract the elements on the diagonal, and if we sum them, get the total number of correctly predicted elements, sum up all the elements in the confusion matrix, and by dividing them we get the accuracy exactly as above. You can simply use something that's already implemented. Accuracy score, we import it also from sklearn-metrics, and then accuracy score asks for two parameters, which are again the same as in the confusion matrix, the ground truth and the predicted values, and is going to give us exactly the same result. So you can use either of these We are not done with training this decision tree classifier. And in order to justify the next step, I want to show you something. So bear with me. What I'm showing you here is how the model predicts on the dataset it has already seen, on the trained dataset. The model predicts perfectly, it doesn't make any error. We can see that all elements are on the diagonal, and the accuracy score is 1, that is 100% accurate. At the same time, on the unseen dataset, the model predicts significantly worse, with an accuracy score of only 61%. This is a clear indication that the classification tree is overfitting the trained data. And overfitting is a serious problem when you want to deploy a model in production, because that's when you want to make sure that your model is going to have good performance, or at least similar performance to what you've trained on, also on new unseen situations or data. In order to increase the predictive power and ensure that our model is able to generalize, we are going to do something that is called cost complexity pruning, which basically means that we are just going to cut some of the branches of the classification trees, reducing the size of our tree. This is going to give us two measures that describe the tree, the CCP alphas and the impurities. Let's display this visually. This plot is very useful in order to help us with pruning or deciding how much of the tree we are going to prune. An alpha of 0 is going to mean that we are not pruning the tree at all. So this is the full tree. And at the full tree, in each one of the leaves, we only leave elements that belong to the same class. So we are not mixing elements from multiple classes. But as our alpha increases, the impurity of leaves starts to increase as well. So we are going to allow some cases to be misclassified. This is going to increase our error at the training time, but is going to help us with the generalization of the algorithm. In order to see which alpha would be the best alpha to use for pruning, we are going to train one model for each of our alphas. Then we are going to look at the performance or at the metrics of the model on the train set and also on the test set. And based on this, we are going to choose the best model. So we are just going to open a list where we will store all our decision tree models, and for each of the alpha we are going to instantiate a decision tree. And then we are going to fit the model on the train dataset. And we are going to append the model to our list of models. So these are all the classifiers, and now we want to compare these classifiers in terms of accuracy for the training and for the testing datasets. And I'll simply use this code that I've written in order to compare the accuracy of all the models that we've trained previously at different alpha points both on the training dataset and on the test dataset. So we can see that the values of the accuracies are quite diverse, ranging from below 60% on the test data up to around 73 or 75%. We are going to choose that model that has the highest accuracy, and we are going to say that that's our preferred classification tree model. How do we know which is that model? So we are going to use this test score list of scores and extract the position at which the score is maximum. Check what's the maximum score. By using enumerate, we are extracting both positions and the value at that particular position. So enumerate is very useful when we need to use the position of a particular element in a list. And we are going to print the position. So for this we are using list comprehension. We're going to print the position if the element I equals the maximum value of the test scores, and the positions are 13 and 14. So there are two models that perform the same on the test dataset, and those are the 13th and 14th model from our CLF's list of trained models. So this is going to be our preferred decision tree classifier, and we can check that the score when predicting on the test dataset is 73%, which is above what we've obtained with the fully grown tree. We can also check how our tree looks like. Okay, so this is going to be our preferred tree. We can also use GraphViz if we want to visualize it more beautifully. But for now, I'm just going to leave it like that and then move on to the next model, which is random forest. And we can use it by importing the random forest classifier from the sklearn ensemble. And exactly the same way we did before, we first initialize the classifier. Here we can pass in different parameters to optimize it, but for now we won't pass anything. And then we can train the model by just using the fit method and passing in the data that we are training on, which is xtrain the features and ytrain the labels from which the model can learn. One thing that I want to pass in here is the OOB score, which is out of bag score. I'll set it to true. This is a performance metric in random forest and I want to check. So now I can first inspect the out of bag score, which is 78%. So this is the first metric. Again, here we didn't perform any optimization or any hyperparameter tuning. We just left everything as default. We want to calculate the accuracy so that we can compare the two classifiers, the random forest classifier and the decision tree classifier. So we are going to calculate a y hat here also, and then pass in the confusion matrix both the y test and the y hat 2, which are the predictions from the random forest classifier. So the confusion matrix is not telling us much. Maybe we just want to calculate the accuracy score. The accuracy score is 61%, which is lower than what we've obtained with the decision tree, and which is lower than what we've obtained even with the full tree, a full decision tree. What we can do next is check which variables were considered most frequently by the random forest algorithm when building its trees, and which are considered to be the most significant variables when classifying. And this can be done by extracting the feature importances from the model and then just visually displaying them with the plot bar, which can be applied on a Panda series. We can see here that the ejection fraction, the serum creatinine, and the age seem to be the most important variables. One thing that we could do in order to try to increase the performance of our model is set a priori the depth of the tree, that is the length of the longest path from the root node to the leaf node, and that is the max depth parameter. This is the maximum number of nodes through which we go from the root node until the last leaf node. Another parameter that we can set is the minimum number of samples to keep in a leaf, how many trees or how many estimators we want the classifier to build before aggregating. The default is 100, but we can just set it to 300 for now. And now let's try and see if this improves our accuracy score, because this is the score based on which we compare our models. Okay, so our model trained, the out-of-bag score went from 0.78 to 0.73, so it's smaller. The accuracy went from 61% to 71%, which is significantly higher. This indicates that basically, like playing around with these hyperparameters and then even more that random forest classifier offers, we have a very good chance of increasing the generalization power of the algorithm. What classifier should we choose? Are we choosing the random forest classifier with a performance of 71% accuracy, or are we choosing the 73% accuracy of the decision trees? Well, there are pros and cons for each one of the algorithms, but I think what's important to keep in mind is also the desire of the customer. So if the customer is going to wish for a model that's very visually appealing and transparent, then for sure you can go with the decision tree classifier. But at the same time, random forests are more robust due to the fact that they aggregate multiple trees, and then you can for sure squeeze more performance from a random forest classifier if you are going to play around with those hyperparameters. But at the same time, random forests will not offer that transparency, so it's more of a black box. I hope today you learned something new, or at least that the exercise that we did together has opened your appetite to learn more about decision trees and random forests. If you want to learn more about data science, or if you are interested in some particular topics, then just let me know in the comment section and I'll try to address it. Keep in mind, practice makes better.